Okay, I suppose I'll get started. So I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis offered by Professor K. Ramesh on the Swayam portal. So today we will be discussing the contents of week 4, which has to do with uh, Jones calculus and light vectors as such. So my name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. I'm working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan from the Civil Engineering Department. So with that, I suppose I'll start. So let us take a look at the first question. It says, at a point in a photoelastic model, the fringe order is found to be 1. So fringe order in photoelasticity is denoted by the letter N. So that the question qualifies that the fringe order is found to be 1. At that point, when a beam of polarized light is passed, the beam gets split into two light rays having a retardation of which of the following is what is asked. So we know that retardation is denoted by delta. Hi, welcome. Are you able to hear me all right? Could you just confirm that, please? Yeah. Very well. Okay, thank you. Yeah. So, so we were just getting started with the first question that says at a point in a photoelastic model, the fringe order is found to be 1. So fringe order is denoted by the letter N. At that point, when a beam of polarized light is passed, the beam gets split into two light rays having a retardation of what? Which of the following? So we know that retardation is denoted by delta. This is nothing but the fraction of a wavelength. Fraction of a wavelength. So when we normalize it, fringe order is nothing but normalized retardation, meaning delta by 2 pi radians. When we normalize that, that is what we denote as fringe order, and it is a unitless quantity, no units. So this fringe order is given to be 1, that is delta by 2 pi is given to be 1. So therefore delta is 2 pi. So what does this mean? Delta is 2 pi. So this means that the fast axis, or the extraordinary ray I should say, or the faster ray exceeds the slower ray by one wavelength. By one wavelength. So that is what is delta equaling 2 pi means, which is denoted by our fringe order equaling 1. Okay, so I'll keep moving. In the meantime, should you have any questions midway, you please feel free to stop me and ask. I'll try to answer them. So the retardation caused on passing a light through a crystal is a function of which of the following? Is it a function of material of the crystal? Is it a function of thickness of the crystal? Is it a function of wavelength of the light? Now we know that let us say that there is a there is an optical element like that. And then light is passed here, which splits into two, and we know that story. So let this be the thickness h of the model. Let us denote that by h. And from here we have the fast and slow ray coming out. So let the retardation be delta. Now we know that time difference between the fast and slow ray is nothing but h by v1 minus h by v2, where v1 is the velocity of faster ray. So speed is distance by time. From that only we are getting this. If both the waves have to travel h distance with a velocity v1 and v2 respectively, so they will take t1 and t2 time respectively. So there will be a time difference. So that time difference is what is h by v1 minus h by v2. Now that time difference we have to convert into frequency, then into cyclical, into the circular frequency. So v2 is velocity of the slower ray. Okay, now what happens is, now we know the time difference. So the time difference is h by v1 minus h by v2. In this, what is the retardation it would have acquired? So delta can be given as 2 pi f into h by v1 minus h by v2. So this is the retardation that it would have acquired, where this is the frequency, where this is our frequency. So this can be recast. Now we know that wavelength into frequency is constant, speed of light. So let us recast this. So we'll get it as 2 pi c by lambda, and let me pull out the h. So it will be 1 by v1 minus 1 by v2, and let me take c inside. So it will be 2 pi h by lambda into c by v1 minus c by v2. Now we know that c by v for any material is the refractive index of that material. And since we are dealing with a birefringent material, there will be two refractive indices, N1 and N2, neta 1, neta 2, however we denote it. So this is essentially 2 pi h by lambda into tau 1 minus neta 2. So this is what the general expression for our retardation is. Now we can see from here, is the retardation dependent on the wavelength, on the thickness, and N1 and N2 are characteristic of that specific material. So from here we can see that it is very much dependent on the material, the thickness, and the wavelength. Hence the answer is all of the above. So I hope this is clear. Okay, so let us move on. Now the material stress optic constant F sigma will be same for the model illuminated using two different light sources is what is given. So here I'll just take this. This is one information that we have. So far so good. So we have been able to relate the retardation to the refractive indices of the of that material for the two rays. Now from photoelasticity theory, actually the N1 minus the normal isotropic refractive index it will have. So that is given by C1 sigma 1 minus C2 sigma 2, and N2 minus N is given by C2 sigma 1 minus is given by C1 sigma 2 minus C2 sigma 1. This is nothing but the it is that material constant which relates its optical properties. One is the transverse effect, one is the longitudinal effect. So here we just have to eliminate. So we have from this expression we can see that we have been able to relate our refractive indices to our principal stresses. So it follows from where we say that if this is related to the retardation. So we can just subtract this out. So we'll get neta 1 minus neta 2 plus neta. I'm just subtracting out both the equations. So C1 sigma 1 minus C2 sigma 2 minus C1 sigma 2 plus C2 sigma 1. So it follows that this cancels out. Neta 2 is, if I take C1 common, I get sigma 1 minus sigma 2. And then if I take C2 common, I get minus, or rather I'll take minus C2 common. So I'll get sigma 1 minus sigma 2. So from here it follows N minus N2 is C1 minus C2 into sigma 1 minus sigma 2. This we denote by some capital C something. Sigma 1 minus sigma 2. So far so good. So we have been able to relate these two quantities. So we know that eta 1 minus neta 2 is this C into sigma 1 minus sigma 2, where this is specific to that material optic relation. And from our previous derivation, we know this quantity. We know this. So what is common in these two? We have this and this the same. So let me just equate that. So delta is 2 pi h by lambda into, I'll just substitute for this. So this will give me capital C into sigma 1 minus sigma 2. So if I simplify this out, so delta is 2 pi h by lambda C into sigma 1 minus sigma 2. I'll just take this to the other side. So if I keep sigma 1 minus sigma 2 in the left side, so what will the right side become? It will be delta by 2 pi into lambda by C into 1 by h. So this quantity is what we term as our n, as we saw in the first question. This quantity is what we term as our f sigma. So this can be recast as sigma 1 minus sigma 2 is n f sigma by h, where sigma 1 and sigma 2 are the in-plane principal stress difference, principal stresses, and sigma 1 and sigma 2 is the difference. This is the fringe order. This is the thickness of specimen or plate or something. And this is the material stress fringe value constant, however we call it. So from here, it is clear that F sigma is this quantity, lambda by C. So let us look at the question. The material stress optic constant F sigma will be same for the model illuminated with two different light sources. So when we say two different light sources, it will have two different wavelengths. If it has two different wavelengths, then F sigma cannot be the same. So F sigma is for a particular wavelength. Where is this important? Now we saw that we generally develop a calibration. For example, for we saw in one of the sessions that we had a light color table where uh, there was one black color in the middle for a beam. Then there was some pinkish color for the fringe order one. Then blue, green, things like that. So this is specific to one light source. Under that light source, we loaded a disk and we generated a calibration table. Not a disk, perhaps a 4-point bent beam because it has straight fringes. So we load that and generate that. So that is specific to that light source. If we have a different light source and we are doing an experiment with a different light source, then it is necessary that we need to generate another color calibration table for that material and that particular light source. So it is dependent on both. So I hope that is clear. Okay, very well. So yeah, so let me move on to the next question. A polycarbonate circular disc, there is a disc of polycarbonate of diameter 60 mm and thickness H is 5.5 mm. A polycarbonate circular disc of diameter 60 mm and thickness 5.5 mm is calibrated in order to find the F sigma value. Okay, so we are trying to find F sigma here. Fine. The monochromatic light source. Monochromatic meaning monochromatic means single color, or in other words, it is a single wavelength, lambda. So for sodium vapor, there is one particular wavelength, 589 or 586 or something, 546 perhaps. So like this, we use monochromatic light source, fine. The monochromatic light source used for the calibration suddenly stopped working. And in order to carry out photoelastic experiments on specimens, one needs to replace the light source. The new light source should be white light source, any light source of monochromatic wavelength, any light source having twice the wavelength of the old one, light source having the same brightness as the old one. So here we essentially want the wavelength to be associated. So at best, if we use another light source of another monochromatic wavelength, let us say, so in a linear relationship, this being, we know that F sigma is, we saw here F sigma is lambda by C. In such a case, F sigma 1 by lambda 1 is F sigma 2 by lambda 2. So with this, at least we can shift it. The best option would be to use the same monochromatic light source that was available. If that not be the case, then we can use another light source which has the monochromatic wavelength, and then we can relate the two. So that is the idea behind this question. Okay, so I take it that that is clear. So let us look at this question. A Moore circle representation of the state of stress is shown in the figure. Now what do we have here? I'll just redraw it quickly. We have the normal stress axis, and then we have the shear stress axis. This is denoted by sigma, denoted by tau. Then we have from here we have something like that. And we know this is in the Moore circle it is 2 theta invariably. And this is given to be the x plane. It says here this is the x plane, this is the y plane. So on the Moore circle every point represents the one particular plane. So as we go around the Moore circle we have traversed all the infinite planes that are possible at one point. Okay, very well. So this is the y plane. Now let us look at the question. A Moore circle representation of the state of stress is shown in the figure. Different stress information obtainable using this along with the experimental technique of photoelasticity are what? Is what is asked. Now what does photoelasticity give us? Photoelasticity is sigma 1 minus sigma 2 is nf sigma by h. We know this. So let us say that we are testing some specimen. At one particular point, we have found out what is the fringe order. Because Moore circle, we are dealing with a point. At that point, what are the infinite planes? That is what we are talking about here. So at that point, we found out the fringe order. We know the material stress fringe value and we know the thickness of that specimen. So essentially, we know sigma 1 minus sigma 2. So this is known. Let me make my pen a little thinner. Yeah. So this is a known quantity from photoelasticity. Now what is asked is with the different information available, what all you can find out. Can you find out the normal stress components, normal stress difference, in plane shear stress, out of plane shear stress is what is asked. So what are the normal stress components here? So we are essentially, it is labeled already that it is X and Y. So we are talking about the XY plane. So we are talking about the XY plane. And let me draw it a little bigger. XY plane. So this is sigma X. This is sigma Y. Why I have drawn it to be negative? Because from the Moore circle, I'm able to see that it is to the left. So that is why I concluded it is negative. And then there is some shear like that. So this is essentially the state of stress for which the Moore circle is drawn. Now what can be obtained from this? So let us look at the Moore circle again. And let me take this. Let me take a copy of this. Okay. So here, this is sigma 1. We know that. This is sigma 2. And since this is the sigma axis and this, or rather this is the tau axis. So what do we know about this? distance from the origin. What is this? This is nothing but my sigma x. Similarly, this is my sigma y. So far so good. Now let us consider this triangle. Let me take some other color. Okay. Let us consider this triangle. And I'll just take that triangle out. In this is 2 theta. What is the value of this? This is nothing but radius of the of Morse circle. And we know radius of the Morse circle is sigma 1 minus sigma 2 by 2. Because we can see from here, this is sigma 1 minus sigma 2. When we take half of that, that gives us the radius of that circle. So that is what is sigma 1 minus sigma 2 by 2. So this we know, sigma 1 minus sigma 2 by 2. Very well. What is this quantity? This is nothing but this, which is tau xy. Because that is how we plot the Morse circle. So this is tau xy. Now, what is this quantity? Now from here, if I take this total distance is nothing but sigma x plus sigma y. That I'm able to see. This total distance is sigma x minus sigma y. I'm sorry. This total distance is sigma x minus sigma y. So in such a case, half of this distance will be sigma x minus sigma y by 2. So this distance is sigma x minus sigma y by 2. And that is all I need now for the calculation. So from this triangle, let me put it here. Yeah. So from the triangle, I can see that what is cos theta by 2? Excuse me. What is cos theta by 2? Cos 2 theta, I mean. Cos is adjacent by hypotenuse, which is sigma x minus sigma y by 2 whole divided by sigma 1 minus sigma 2 by 2. So this gives me sigma 1 minus sigma 2 by, yes, I'm sorry. Yeah. So from here we get sigma 1 minus sigma 2 by 2 into cos 2 theta is sigma x minus sigma y by 2. Or in other words, sigma x minus sigma y is nothing but sigma 1 minus sigma 2 by 2, or sigma 1 minus sigma 2 cos 2 theta. And we know sigma 1 minus sigma 2 from photoelasticity. So once we know theta, we can calculate sigma x minus sigma y. And theta also we can calculate using photoelasticity from the isoclinic fringes. So normal stress difference we can get. Similarly, from the triangle, I took cos 2 theta. If I take sin 2 theta, sin 2 theta is tau xy upon sigma 1 minus sigma 2 by 2. So this comes out to be tau xy equal to sigma 1 minus sigma 2 by 2 sin 2 theta. So from photoelasticity directly, it is just a constant. We can actually get the in-plane shear stresses. In-plane shear stress we can get. Can we get out of plane shear stress? Out of essentially what we are trying to know is when we have a Mohr circle like this is for the 2 dimensions. Another Mohr circle will be like that, and the third one will be like this. These are the three Mohr circles that represent the all the three dimensions. So since we do not know sigma x and sigma y separately, it is not possible for us to calculate that. So out of plane shear stress and normal stress components we cannot directly calculate. Now we know that sigma x, from here we found that sigma x minus sigma y, we have one expression. If we can get an expression for sigma x plus sigma y, then we can go for stress separation. We can get sigma x, sigma y, and tau xy we have already got here. In the cases where if we were to measure, let us say, this is out of the scope of this question, but I'm just explaining this. Let us say that we have the disk and we loaded it and we were to measure the out of plane strain. Now we know that Ez, if this is xy, if this is xy, Ezz is nothing but sigma zz by E minus mu by E into sigma xx plus sigma yy. I'm just using double subscripts. Single or double doesn't matter that much. Now for a plane stress problem, sigma zz is 0. So if I have the out of plane strain, then sigma x plus sigma y I can get. Or in other words, I can get sigma x plus sigma y equaling minus E epsilon zz by mu. So if I measure by some means out of plane strain, then I have the expression for sigma x plus sigma y. And from photoelasticity, I have the expression for sigma x minus sigma y. I can add these two and I will be able to separate out the stress and obtain them as sigma x, sigma y, and tau xy. So this is just a small aside for this. But otherwise we can, so for stress, normal stress components, we need some additional information, but normal stress difference we can definitely get from photoelasticity. Okay, I hope that is clear. Are there any questions in what we discussed? Yes, sir, please go ahead. Yes, yes, isoclinics. Yeah, yes, 2 theta we will come to know. Using isoclinics, yes. Exactly. Yeah. So 2 theta we know, sigma 1 minus sigma 2 we know. So from here, sigma x minus sigma y we know. We should be able to, which one? Yes. Yeah. Yeah. Circle as a whole is not located. Separately, you cannot get. Only the difference you will be able to find out. This expression, how it got derived, that was why I had the more circle there. But essentially, the information here is that sigma x minus sigma y, sigma 1 minus sigma 2, and theta. These two I can get from photoelasticity. So at best, using the power of Mohr circle, I can get sigma x minus sigma y. Yeah. So this expression holds good even if this circle was shifted, even if it was like this. So then also this holds. So that is a general case. I hope you understand. Yeah. Yeah. Very good. Okay. So let us look at this question. Which of the following statements are true? Isochromatics are wavelength dependent. Isoclinics are wavelength dependent. Isoclinics are formed when the fast axis in the stressed model align with the polarizing element. Under a monochromatic or a polychromatic light source, the isoclinic viewed will be different. Now, let us understand one thing. Let us say that there is a light source, and then I have a polarizer like that. And then I have a model here. So here we are looking at some point, some general point. And I have my analyzer like this, which is crossed, which is a crossed polarizer. Now let us say that at this point, the actual fast and slow axes are like this, fast and slow. Now the question asks, let us look at option C first. It says the isoclinic formed as the fast axis of the stressed model align with the polarizing element. So let us say that this was the case, that the fast axis aligns with the polarizing element. Both are aligned. So what will happen is the light that comes through this, that is plane polarized, will pass unaltered through this point because the fast axis is aligned, and will get totally cut, because the analyzer is crossed. In such a case, at this point, we'll be having a fringe like that, where this is that point. So we will be having no intensity of light coming through that point. We will have a dark band over there. So that is what isoclinic is. So this is correct. Isoclinics are formed when the fast axis of the stressed model align with the polarizing element. Another way to phrase this is that slow axis is aligned with the polarizing element. And we know that the maximum and minimum principal stress directions, they are mutually perpendicular. So it doesn't matter whether fast is aligned or slow is aligned. Very well. So isoclinic is wavelength dependent. Isoclinic is formed because the light passes unaltered and gets cut because it is viewed through an analyzer. So isoclinic is not wavelength dependent. Isoclinic is formed because, as it is said in the next option, it is formed because the fast or slow axis of the stressed model is aligned with the polarizing and analyzing elements. So that is why isoclinic is formed. So it is not wavelength dependent. Isochromatic, on the other hand, isochromatic is nothing but N or delta. So that we saw that sigma 1 minus sigma 2 is N F sigma by H, or rather, let me not take this one. Let me take we had this delta is 2 pi, one expression we had here. We had derived it, this one. This one. We are able to see that isochromatics are formed because of retardation brought about by the stresses, which is a function of the wavelength, as we can see. So isochromatics are a function of the wavelength. What does that mean? If we were to change the light source of a different wavelength, then we will be seeing different colors of isochromatic. If it is a monochromatic light source, then we will be seeing only one color. If we use a polychromatic light source, then we will be seeing different colors in a form of fringes. So that is what this means. The last option is under the monochromatic and polychromatic light source, the isoclinic viewed will be different. Now we saw that isoclinic is wavelength independent. So what does that mean? When we have a monochromatic and polychromatic light source, what is essentially changing between these two? The light source, the wavelength of the light. And since isoclinic is not dependent on that, under monochromatic and polychromatic light source, the isoclinic viewed will be the same. So even if I were to take this light source and put a white light source instead, this I will still see as a black band only. And why is it black? Because not because of retardation, it is because the light is getting cut there totally. So that is why this is black. There is no light entering from that point. So this is one way to differentiate between isoclinics and isochromatic fringes. That we load a model in a plane polariscope, we see two types of fringes. Now if I were to change the wavelength of the light, only isochromatics will change color. Isoclinics will still remain the same. On the other hand, if we want to move the isoclinics and not the isochromatics, what can we do? We can change this orientation. Let us say I rotated these two, analyzer and polarizer. Now at some other point, the fast and slow axis will be like this, where again the light will pass unaltered. So the fringe from here, I'll see that the fringe would have moved here. So there'll be a movement in the isoclinic fringes that I'll observe when I actually rotate the analyzer polarizer crossed combination. So that is another way to differentiate between isochromatic and isoclinic fringes. So by this I mean it's an isoclinic fringe. So I take it that is clear. If there are questions, please feel free to ask. So this is not right. Okay, so let us look at the next question. Which of the following, yeah, we had to select the true ones. That's fine. Which of the following statements are true? Isoclinics are formed when the fast axis in the stress model align with the polarizing element. This option seems to be the same, repeated one. So we know that that is right. Under a monochromatic light source, Again, this option is also repeated. In conventional photoelasticity, polarizer and analyzer are always crossed. This is true. Let us say that we had a polarizer like this and we did not cross the analyzer. So there is nothing we can make out from here. Essentially, in conventional photoelasticity, a plain polariscope with just a polarizing and analyzing element were used to determine the isoclinics. In such a case, if I don't keep it crossed, wherever the fast axis is aligned with the model's fast axis, the light will pass and it will not get fully cut. Some component of the light will still pass, and I'll be able to see some grayscale fringes. It won't be a perfectly dark fringe. So in that case, I will not be able to distinguish and identify between them. So that is why these are kept crossed. Using suitable optical arrangement, isoclinics can be viewed separately. Now there is actually no optical arrangement that can give us isoclinics separately. So isoclinic is fast and slow axis direction dependent. And this is getting formed because plane polarized light is passing unaltered through the model, I shouldn't say model, through the point of interest. And gets cut. And gets cut by the analyzer. This is only happening because polarizer is perpendicular to the analyzer. Now let us say that we introduce some elements here such that the light doesn't, this light is no longer plane polarized, so that this light is no longer plane polarized but is something else, let us say circularly polarized light. In such a case, the directional dependence totally goes. So when you are impinging a circularly polarized light, there is no plane polarized light that is getting impinged on the model. So the fast axis, there is no light that will pass unaltered through the fast axis. In essence, there we are actually removing the directional dependence of any sort when we bring in circularly polarized light instead of plane polarized light. So that is what is the essence behind the circular polariscope, which we will see next week. In such a case, in a circular polariscope, we will be able to observe just isochromatic fringes, which are wavelength dependent. So isoclinic fringes can be eliminated totally by bringing in modifications to the polariscope. However, there is no separate arrangement where only isoclinics can be viewed, because once you stress the model, by its very nature, it is birefringent. So if fast and slow axis is brought about by the stress, naturally there will be retardation brought about by that stress, and that retardation has to form isochromatic fringes. So there is no way for us to see only the isoclinics. So I take it that that is clear. And also there is no optical arrangement which can give you all the isoclinics at once. How do we see isoclinics for different degrees? For example, if this is the plane polariscope and this is the model, when I keep it like this, I'll be able to see 0-degree isoclinics. When I keep it like that, move it in a crossed manner, then I'll be seeing 30-degree isoclinics and so on as we move it in steps. So there is no arrangement that can give me all the isoclinics at once. Granted, I can take images of all the isoclinics and then perhaps superimpose that or something like that. But as such, there is no arrangement which can give all of this readily. It has to be seen one after the other. Okay, very well. So I hope this is clear. So let us look at this question. A model, a model is viewed using a plane polariscope arrangement. Fine. So we have a, why don't I take this from, yeah. So this is my plane polariscope. Okay. By rotating the polarizer analyzer combination kept crossed by 30 degrees from the reference axis. So what we are saying is this we have shifted to this point. This is 30 degrees. So this is 30 degrees. Hence this also I should rotate because these are kept crossed. So this is my analyzer. This is also 30 degrees is what we are saying. One can view the points in the model where the principal stresses are oriented at dash degrees from the reference axis. So at some point, there will be the fast and slow axis will be like that. So once the plane polarized light comes at 30 degrees, it passes unaltered through the fast axis and it will get totally cut by the analyzer. So we will be seeing a fringe there. So this will form a fringe there. So that isoclinic will belong to which angle is what is asked. So it is but obvious that it will belong to the 30-degree isoclinic. So I hope this is clear. Okay. So let us look at this question. Along the isoclinic contours, what is true? Principal stress orientation is constant. Principal stress orientation is different. Individual value of principal stresses are same. Principal stress difference is same. So what this says is this is sigma 1 minus sigma 2 is constant. This says sigma 1 is constant. Sigma 2 is constant. This says theta 1 and theta 2 are different. This says theta 1 and theta 2 are same. Now we know that isoclinic does not have anything to do with the principal stress difference, but only the orientation. So it has to be one option A or B. And we know contour, when we say it essentially links only the points where some parameter value is same. So principal stress orientation, wherever it is same, it is linked. And even in the lecture for one fringe, isoclinic fringe that is shown here. So there may be a point here where our fast axis is like that, slow is like that. Then there will be some other point where this will be fast, this will be slow. The only common thing is that both are oriented in the same direction. So the principal stress orientation is the same. The difference might not be the same. I hope that is clear. So this is an isoclinic fringe. Okay. Two rectangular specimens, one made of mild steel. So let us draw the rectangular specimen. Okay. So this is made of mild steel. Yield strength is 80 MPa. So this is my mild steel. Fine. And this is aluminum. The yield strength of 15 MPa. Okay. So these two have a cross section of 100 by 10. So this, if this is 10, this is 100. It is not drawn to scale. You can consider it to be drawn to scale. Are subjected to a tension of 50 Newton. Fine. 50 Newton. Both are subjected. Okay. With this information, select which of the following statement is true. Within the elastic limit, the stresses produced in both the materials are same. So under uniaxial tension, we know stress is, or why do we have to do that? Rather, let me take this point. At that point, what is the stress tensor like? In two dimension, stress tensor is 0, 0, 0, and then 50 by 100 into 10, and not 100 into 10, 10 into some thickness. Let us take the thickness to be unity. So it is just 50 by 10, which is 5. So this is my stress tensor here. Same will be the stress tensor here also. And since this is uniaxial tension, away from the loading points, at every point the stress tensor will remain the same. So stress in both the materials is same. Within the elastic limit, the strains produced are same. Now, if we take the graph of mild steel, it is like this. E is 210 around. And this is only one third. Aluminium is only one third. It has E around 70 GPa or so. So this is the stress strain curve like. Now if the stress in both the case are same, can the strain also be same? Essentially what I'm trying to say is this is the line representing the same stress in both the materials, which is 5 MPa, let us say. In such a case, strain in steel is this much, strain in aluminum is higher. So strains are not the same. Mild steel will fail faster than aluminum. By failure in this context, since yield is given, so we consider yield to be the failure. So when both are loaded identically, naturally the one with a higher yield strength will fail later. So aluminum will fail faster than mild steel. Stress induced in both the materials can be viewed directly using the naked eye. Can stress be viewed is a question. No, we are not using any polariscope here. It just says that we are viewing the model. So stress, force, these are all abstractions. These are mathematical. These are mathematical constructs. They are not measurable. That is, we have to measure something else to measure them. Generally, in most of the experimental techniques, we will measure strain, then or displacement. From there, we will come to stress using the constitutive relation. However, photoelasticity happens to be a method where we don't need to measure strain. We can measure the stress, but through light intensity. So there also there is one step that is taking place. So there is always one step to this. So these cannot be viewed. Appropriate stress contour produced in both the materials can be visualized using experimental techniques with the help of suitable models. So what is it that we expect to see in this case? Let us just do a thought experiment. Let us say that I take this. Let us say I take this specimen and I pull it like this. And let us say that I am viewing this using a polariscope. So what is sigma 1? Throughout the model domain, except for the loading points, which we are obviously not considering, sigma 1 is nothing but 5 MPa. This 5 MPa, I hope you know where that 5 came from. It is coming from here, which is 50 by 100, and I'm taking thickness to be unity. Oh, rather it should be 0.5 actually, not 5, because it is 50 by 100. 0.5. Is there anywhere else I have written? 0.5. Okay. So this is 0.5 MPa throughout. Sigma 2 is 0. So sigma 1 minus sigma 2 is 0.5. For this, we have taken the thickness to be unity. And this is MPa. So from stress optic law, which says sigma 1 minus sigma 2 is nothing but n f sigma by h or t, whatever. So here this gives us 0.5 is nothing but n f sigma by 1. So it is n f sigma. And f sigma for this material is constant, let us say. So when f sigma is constant, therefore n is constant. N is constant. So I will just see a uniform color throughout. That is what I anticipate to see. In a white light setting, I'll see a uniform color. But there is a catch here. Actually speaking, these are mild steel and aluminum specimens. These are not birefringent materials actually. So what we will have to do is, uh, that is why it says can be visualized using with suitable models. Why we are saying suitable models? Because stress is not dependent on the material property as we saw. For a plane stress problem, if I were to take an aluminum rectangle, or if I were to take an epoxy or a polycarbonate rectangle, in both the models, the stresses induced will be same. It is not dependent on the material. So even if I were to study epoxy with the say under the same loading conditions, I will get a similar stress that will actually be induced in the aluminum case. But strains naturally will not be the same. I hope that is clear. If there are any questions, you please feel free to ask. Okay, very well. So let us move on to this question. The figure shows a disk made of different material indicated by the Roman numerals 1, 2 to 5 under diametral compression and under the same loading conditions. So it is just a matter of changing the material, loading, everything remains the same. In the table, F sigma values of different materials and the letter A, B, C, D, E are provided. The fringe order at the center of the disk is given. So here we are able to see, here we can see N is 2.83, 4.25 and so on. With the help of this information, identify what is the material of each of the disks. This is what is given. Now let us take a look at this. There is a disk and it is loaded under the same condition. Only the material is changed. But we saw that stress is not dependent on the material. In such a case, for any material I take, stress should be the same, which means sigma 1 minus sigma 2 is constant for all disks. And we know that sigma 1 minus sigma 2 is nothing but n f sigma by h. And since everything, all the loading conditions are same, only the material is changing. So we take it that h into sigma 1 minus sigma 2 is constant, which is nothing but nf sigma. So from here, we get that nf sigma is some constant. N f sigma is, so this is nothing but a rectangular hyperbola like that. So the curve would be like that. So wherever n is more, f sigma has to be less. Wherever n is less, f sigma has to be more. So if I were to arrange letter A to E in the order in which their f sigmas are, so let me put it here. So f sigma of A, B, let me write it like this, A, E. So out of this, which is the maximum? I can see that E is the maximum, which is greater than, which is the next one? Home light, C is the next, which is followed by epoxy A, which is followed by polycarbonate B, which is followed by D. So this is the decreasing order of F sigma. So from our equation that this is a if this is decreasing, if f sigma is in the decreasing order, then n has to be in the increasing order. So let us say, uh, let me write n1. Actually, it's not given in a table. That's why it is a little inconvenient. Okay, n is n for 1 is 2.83, n for 2 is 4.25, n for 3 is 0.11, n for 4 is 1.31, n for 5 is 169.77. So let me take this information here and let me arrange this in the, so that was the decreasing order, so this has to be the increasing order. So in the increasing order, n1 followed by this 2 followed by this followed by this, ultimately followed by this. So from here we can directly draw the correlation. Yeah. So E is 3. I hope you are able to understand what I'm saying. This correlation we can draw. E is 3, C is 4, A is 1, B is 2, and D is 5. So anyway, that is what is asked. So I have not put those questions. So it just asked to identify, enter the correct uh, letter representing each of the materials. So A to E materials are given and we can identify which are the materials. So I hope that is clear. Okay, so let us look at this question. An epoxy disc is subjected to diametral compression. Again, we came to the problem of a diametral compression. And this is epoxy, which has a diameter of 60 and F sigma of 12.5. Okay, load is 300 and the fringe order was found to be 1.5 at a particular point in the model. So let us take that point to be this. Here, the fringe order comes out to be 1.5 is what is given. Similar experiment with the same geometry is conducted on a polycarbonate disc. So here, this is polycarbonate. I'll just erase this. This is polycarbonate, which has an F sigma of 8.5. What would be the fringe order? What is this value? N is what? Naturally, we have seen that If F sigma is different, N also will be different. And we saw from the just the previous problem, we saw that this is constant. In such a case, N epoxy F sigma epoxy must be equal to N polycarbonate F sigma of polycarbonate. So what is N of epoxy? At that point it is 1.5 into epoxy's F sigma is 12.5. N in poly is what we are trying to find into 8.5. So from here we can find out that N in polycarbonate would be, what will this be? 12.5 into 1.5 by 8.5, it is 2.206. So this is the, this will be the fringe order if we change, keeping everything same, if we just change the material to polycarbonate, the fringe order there will be 2.206. Why? Because stress would have to be the same. Since F sigma is different, the fringe order has to adjust to that to maintain the same stress. So I hope that is clear. Very well. So let us move on to this question. A model is viewed through a plane polariscope arrangement. Okay. The fast axis at the point on the model coincides with the polarizing axis. The fast axis coincides with the polarizing axis. Fine. The retardation introduced at that point is delta equal to pi. So retardation is given to be delta equal to pi. What does this mean? The fringe order is delta by 2 pi. So fringe order is 0.5 at that point. Fine. So this much we know now. Consider only the real part of the linearly polarized light k e power I omega t coming out of the polarizer with k as unity. Okay. K is taken to be 1. Take omega t equal to pi by 4. Take E2, E3 as the slow and fast axis respectively at the start of the model. Take E4 and E5 as the slow and fast axis at the end of the model. So what are we trying to say here? So we have this line. We have this E1. This is the polarizer, first polarizer. Then we come here, we have two axes that are aligned at some theta to the datum, to the polarizing axis. And it is actually given here in this question that the fast axis at this point coincides with the polarizer axis. What does that mean? That the slow axis coincides with the analyzer axis. So essentially, the implication of this statement is that theta is 0. So it is kept parallel to that. That is what is said in the question. And the model starts at this point. The model ends at this point. So in between these two, a retardation is brought about. So that is what is said. Okay. Now what do we need to find out here? Find out the magnitude of light vector coming out of the polarizer. So the magnitude of the light vector coming out of the polarizer. So what is asked is E1 is asked. E1's magnitude is asked. So E1 is nothing but the real part of this. So I will have essentially K is unity, so this will just be cos omega t. And since magnitude is asked, it will be cos square omega t. In the question, omega t is given to be pi by 4. So this is nothing but cos square pi by 4. Cos pi by 4 square. I'm sorry, magnitude of the light vector. E1 is only asked. It is not the intensity. It is the magnitude of this light vector. So this is nothing but cos pi by 4. So cos pi by 4 comes to, it is cos 45. So it will be point. Okay. Find out the magnitude of light vector coming out of the model at the point of interest through the fast axis E5. Now we know that E5 E5 is parallel to the polarizer because E3 is parallel to the polarizer. So therefore theta is 0. Okay. Now what we can do is, let us say that we have E3 here actually. This is our E3. This is our E2 for this problem where it is kept at 0. And then there is a retardation brought about, and this is my E5. This is my E6. Sorry, E4. And then I have a analyzer that is kept like this, which is E6. So to be problem specific, this is what the diagram is because it is kept at 0 degrees. At that point, it is 0. Fast axis at that point coincides with the polarizing axis. Okay. So we have light passing the E1, light from E1 passes through E3 and then acquires a retardation as it goes to E5. So what will that E5 be? So E5 is nothing but E3 plus that retardation added with that retardation. So we can take this to be cos, since the input light is, this is cos omega t. So this is nothing but E5 is nothing but cos omega t plus delta by 2. And E4 will be cos omega t minus delta by 2. Since this is what is happening. Otherwise, there would have been a sine and cos cos component. Since that is not present, actually it will be the other way around. First will be cos. So E5 is nothing but cos omega t plus delta by 2. So this comes to cos of omega t is pi by 4 plus delta by 2. Delta is pi, so this is delta by 2. So what does this come out to be? Pi by 4 plus pi by 2 cos of answer. So this comes out to be minus 0.707. Now the last question asks, what is the magnitude of the light vector coming out of the analyzer? We can clearly see here that our polarizer is kept like that. E3 is E3, E5 is parallel to the polarizer. E2, E4 is perpendicular to it. In such a case, if E5 comes out in full, then naturally E6 would have to be 0. I hope that is clear. What I mean to say is the light that was like this, it got fully resolved into E3 only. So essentially E2 here is 0. Similarly, E4 here is 0. So E6, there is no light actually coming out. And this can be seen without going into this mathematics also, this can be seen. What does our question say? That it is a plane polariscope arrangement. And at that point, the fast axis coincides with the polarizer axis. So this is a point where the isoclinic fringe will get formed. And what we are asking is, what is the output light that we want to see? Out of the analyzer, what will I see? I will see that point to be sitting on an isoclinic fringe, which means that the intensity is 0. There will be no light coming towards me. Hence, this is 0. I hope that is clear. So even even with the knowledge of our plane polariscope and isoclinics, we can see that the light that will come out will be 0 because this point specifically sits on an isoclinic fringe. So I hope this is clear. So anyway, so now I have run out of questions. If there are any questions, please feel free to ask. Okay, well, if there are no questions, you can we can consider ending the session. If there are any questions, I can take them now. If there are no further questions, then let us call it a day. I'll see you people in the next Monday meeting where we will be discussing week 5. So if there are no questions, we'll end it. Yes, sir. Yeah, thank you. Thank you very much. Okay.